Hello, everyone. So first of all, sorry, it is cold, but they are fixing it right now. So it will be warmer during this seminar. I hope so. Okay, so today we have Álvaro López-Gallifa, and I'm going to present it. It's a pleasure for me since he started his PhD, I think 1 year after I arrived here. So yeah. So he obtained his physics degree and astrophysics master's degree from the Universidad Complutense de Madrid. He then worked for a year at the same university as a research support personnel with David Montes. After that, he started his PhD here in astrochemistry, supervised by Dr. Victor Rivilla. He completed 2 internships, one at the Osservatorio Astrofisico di Arcetri in Florence, in Italy, during 2 months under the supervision of Dr. Maite Beltran, and another one at the European Southern Observatory, ESO, during 9 months in Santiago de Chile. And the latter was funded by an ESO studentship, and it was supervised by Sergio Martin. He has now submitted recently his PhD thesis, and the expected defense date will be in January. And today is going to talk about this, in particular about comparative study of the full chemical feedstock of galactic and extragalactic star-forming regions. Go ahead.
Okay, I think this thing is working. Yes, good, perfect. Well, so first of all, thank you everyone for joining here. I am very happy to share my thesis with all of you. So let's start it. First of all, this thesis, it's okay. Yes, let's start with the outline. So this presentation is about my PhD thesis, and it's going to be divided in first of all the first 3 slots, which are going to be the scientific context and the objectives, and a little bit the methodology, all the tools that we will use to detect molecules on different sources. Then we have the 3 main points, which are 4, 5, and 6, which are three scientific articles that compose my thesis, and finally conclusions and future perspectives. Let's start with the scientific context. And this thesis is going to be mainly about the interstellar medium. And what is the interstellar medium? The interstellar medium are all the ingredients which are in between the stars. The interstellar medium is mainly composed of gas and dust. Gas is 99% of the mass of the interstellar medium, and it's mainly composed of atoms and molecules. And then we have the dust, which is pretty important despite only being 1% on mass. The dust is composed of small grains of solid material. So to dig a little bit more, we have the interstellar gas. It's mainly composed of hydrogen and helium, and just a 2% of carbon, oxygen, or nitrogen. And also we have the interstellar dust, which is pretty important because it creates the extinction of light, and also is key to form molecules. So one stage of the interstellar medium are the molecular clouds. These molecular clouds are overdense areas of the interstellar medium. They compose 50% the mass of the interstellar medium, and they are mainly composed of H2. But most importantly, they are the birth site of the stars. The stars are going to born from these molecular clouds. And these molecular clouds will trigger the first step of the interstellar cycle of matter. In first step, we have the molecular clouds, and when they start to condense, they will create filaments, and within those filaments, new protostars will be born. With these protostars, when they cluster, we have the star-forming regions. So the star-forming regions are mainly composed of protostars. But those protostars, due to its magnetic field and its gravity, can create some outflows. Those protostars will eject some material. And when this material encounters some dense parts of the interstellar medium, it will create a shock region. Then, if we just focusing in one star, we will go to the protoplanetary disk phase, in which we have the protostar, and then a disk is starting to be formed. Within this disk, protoplanets will be created, and asteroid planets, and also comets are formed from here. Comets are important because they are pristine relics. They can help us to know which was the chemistry in early stages. Then, moving on to the planetary system, once the star is born and when the protoplanetary disk is clear, we have the planetary system. And at the end of the life of the star, it will eject all the mass and it will eject all this material again to the molecular cloud, restarting the cycle again. So, in this work, star-forming regions are pretty important. That's why I will distinguish two types of star-forming regions: low-mass star-forming regions and high-mass. Low-mass star-forming regions are composed of low-mass stars, which are stars which have less than 8 solar masses of mass. And also, they are important because they are pretty similar to the Sun in terms of mass. And high-mass star-forming regions, they are composed of a lot of big stars which have more than 8 solar masses, and most importantly, they are the birth environment of the solar system. So I explained all the physical steps that a planetary system needs to be born, which are these four. However, what happens with the chemistry? We are more focused on the chemical part. So we would like to ask to ourselves if there is any chemical threat. What happens with the molecules that conform all of these sources? Are these molecules inherited? They are reset? What happened with them? So for that, we will use the astrochemistry. Astrochemistry is focused on studying the abundances and all the reactions that happens in the interstellar medium. So thanks to astrochemistry, we will be able to characterize the sources and to retrieve properties. So nowadays, we know that the interstellar medium, indeed, it's chemically rich. Nowadays, there have been about 340 molecules detected with increasing complexity. And as you can see here, nowadays we are detecting more molecules than ever. We are in a golden area in astrochemistry. And we have detected a wide variety of molecules. We have molecules from 2 to 13 or more atoms. That for us, it's pretty complex. So now we know that we have this chemical complexity in the interstellar medium. But how is this formed? How do we explain all this formation of these complex molecules in the interstellar medium? So basically, in the interstellar medium, we have two types of chemistry, two types of reactions. We have gas phase and grain surface reactions. Gas phase chemistry is basically when the molecules encounter in the space. These molecules are going to interact by creating new molecules, dissolving molecules, or creating new ones, which are the bond formation, bond destruction, and bond rearrangement. However, not only the gas phase is important here. We also have the grain surface chemistry. The grains, as I mentioned to you before, they are pretty important to form molecules. Why? Because in the grains, the molecules can be sticked. The molecules will land onto the grains and they can interact with other molecules that already landed in the grain. So they can interact, and once they interact, they can be ejected again in the interstellar medium, which are these phases that we have here. So we have these two types of chemical reactions in the ISM. Also, the fact that we know that we have such a huge complexity with having detected molecules of more than 10 atoms, we can ask to ourselves what happened with the prebiotic molecules, with the molecules that can trigger the origin of life. So to try to explain this, there are two theories nowadays. We have the endogenous synthesis and we have the exogenous delivery. Endogenous synthesis supports the theory that the molecules that were already at Earth, and thanks to local phenomena such as volcanoes or photochemistry, the molecules can evolve and then it can form the life. However, with the exogenous delivery theory, it explains that we need the impact of some meteorites in the young Earth, and those impacts can trigger new chemical reactions that will help to the trigger of life at Earth. And also, these meteorites could bring some new materials from the other parts of the interstellar medium. Okay, so we know again that we have a huge complexity. And we have detected these 340 molecules in a wide variety of sources. So in the past, there have been some scientists that has probably tried to make some comparative studies. They just took, in this case, two molecules, methylformate and dimethyl ether, and they just compare the ratio in a wide, in a wide variety of sources, which are all of these. And they found that, for example, this ratio is quite similar. All the sources are within a ratio of 2. Also, we can do the other scientists made a complete different thing. They only took two sources, in this case, this comet and this star-forming region, or this comet and this star-forming region, and they compare with a lot of molecules. Each point corresponds to a molecule, obtaining pretty decent correlations. Okay, so what do we want to achieve here in this thesis? We would like to answer these questions. First of all, we would like to know the full chemical feedstock of star-forming regions. This is important because our sun was born in these high-mass star-forming regions. So to know what molecules were there, when our sun was born, it will give us some crucial hints. Also, we would like to know how this chemistry evolves dependently on the stage of solar system formation, to know if the molecules are heritaged or not. Also, what happens when we change the physical conditions, when we change the source, when we change the chemistry, what happens to the molecules that we are detecting? And finally, all the three questions of above, we will study only galactic sources, but what will happen when we go one step further and we go to other galaxies? Is the chemistry in other galaxies similar to this one, or it's a completely different story? Okay, so the objectives of this thesis, they are based on detecting a high amount of molecules. So how do we detect molecules? For detecting molecules, we need these three parts of this triangle. We need molecular spectroscopy, observations, and fitting analysis. So let's start with the molecular spectroscopy. So molecules emit in different types of transitions. We have electronic transitions that are triggered due to the movement of the electrons. We have vibrational transitions, which are triggered due to the movements of the nuclei of the atoms within with the tiny movements of the nuclei of the atom, and also we have the rotational transitions. The rotational transitions are really important for us because it's when the molecule moves as a whole, and this movement of this molecule will trigger some transitions. And as you can see, each transition is triggered at a different temperature, and we are studying the interstellar medium, which is pretty cold, which means that most likely we will be able to detect rotational transitions. And how do we know which transitions correspond to each molecule? In this case, we need the help of people from the lab. We need the help from spectroscopists. They will characterize the molecule that we will like to search in the interstellar medium. They will retrieve key parameters such as the rest frequency, the energy of its transition, the Einstein coefficients, etc. And also, all of this information is available in online catalogs, such as CDMS, JPL, or LSD. So once we know which transitions correspond to each molecule theoretically in the lab, and we know for which frequency to look for, we need to have observations. We need to observe the region that we will want to characterize. And as I mentioned before, we will be focused on the rotational transitions. So these rotational transitions mostly emit on the radio wavelengths, which means that during this thesis we are going to be focused on the radio wavelength regime. And the fact that we're focused on the radio wavelength regime implies that the atmosphere is totally transparent, which means that we can have cutting-edge telescopes ground-based, which means that all the most powerful telescopes are here at Earth. And we will use basically this telescope, this interferometer, which is ALMA. When we detect molecules with ALMA, we are not only taking into account this antenna, but all of this array of antennas. The interferometry, this interferometer takes into account all the antennas, and it creates a huge one, which will help us to have better information. Also, we need unbiased spectral surveys. So we need to observe one source in detail during a high amount of time to be able to retrieve enough transitions and enough molecules to detect them. We would like to have a large spectral coverage. We would like to be observing a huge amount of wavelengths, because if we do that, a lot of transitions will be there, and we could detect the molecules more firmly. And also, we would like to have high sensitivity. We would like to detect the tiniest transitions to detect as many molecules as we can. And also, we will be able to detect isotopologues. Isotopologues are molecules where one atom is one isotope. So you change the number of neutrons of some atoms within the molecule. So if we do that, we will have a large sample of molecules, an homogeneous data set. And this is key, because we would like to have a lot of molecules on the same source being obtained in an homogeneous way to have reliable values when we compare with other regions. So this is an example of one spectrum that we have obtained. And as you can see here, we can see some possible transitions which can correspond to some molecules. But how do we know which transition corresponds to each molecule? Let's put one example. If we took these lines and these lines, which are these two, we have this. So we can ask to ourselves, okay, to what molecule corresponds this? So to answer that, we need the last part of our analysis, the fitting analysis. First of all, we need to look where are some theoretical transitions of some molecules that we already know, which are marked with the dotted red points. And also, we would like to apply an local thermodynamic equilibrium approximation. We would like to fit the Gaussians with we would like to fit a model with Gaussians with respect to the observed spectrum, which is plotted in black. And we use local thermodynamic equilibrium, which means that we consider that the source is thermalized, which means that with only one temperature, we can characterize the source. Okay, but this is one way of doing it by hand, just to try to search manually which transitions corresponds to which molecules. However, we have a huge coverage, and we have a huge possible of transitions to analyze. So we need the help of a software, which is MATCUBA software. MATCUBA software is developed in our group here at Centro de Astrobiología, and it creates a synthetic spectrum by solving the radiative transfer equation and applying again LTE approximation. So MATCUBA creates a model which is plotted here in red, and this model must be as close as possible with respect to the observed source. So when they are too close, it means that we have fully characterized this source. However, you have to introduce in MATCUBA one by one the molecules that you want to detect. So when you are adding more and more molecules to MATCUBA, the synthetic spectrum will be more crowded, and thus it will be more similar with respect to the observed spectrum. So MATCUBA takes into account 4 physical parameters, which are excitation temperature, column density, radial velocity, and full Wilhelm maximum. Basically, column density is the number of molecules that we have in that source. And if you see, when we change the log n, in this case, the more is the value, the more intense are the transitions, which makes sense because there are more molecules, and these more molecules emit more amount of photons. And also we have the excitation temperature. This excitation temperature is sensitive to the energy of its transition, because as you can see here, in this case at 30 Kelvin, these transitions get really intense, but at 100, this is way less intense. Also, MATCUBA takes into account the radial velocity, which basically shifts the observed spectrum with the synthetic spectrum, and also this shift can help us to determine the radial velocity of the source. And finally, we have the full Wilhelm maximum, that it basically changes the width of the lines that we are detecting. So MATCUBA takes all the things that I have previously mentioned in this analysis, and it takes the molecular databases, the data cubes with with the observational information, and it takes into account the formalism, and it mixes everything. And once we start adding molecules in MATCUBA, automatically it will retrieve the molecular parameters I previously mentioned, also molecular abundances ratios, because these values, these ratios between column densities, they are going to be really interesting for us to compare with other sources. And also it will retrieve us a molecular census. And MATCUBA plots this kind of panels which help us to determine if the molecule has been well detected or not. Okay, so once we have detected a high number of molecules in one source, we would like to know how to compare the chemistry of one source with the chemistry with other source. So these plots, I am going to be showing these plots throughout all these presentations. So these plots, in each axis, we have a different source, and each point corresponds to one molecule detected in both sources. Also, they are color-coded by bearing families, depending if they are composed of oxygen, nitrogen, barium, sulfur, etc. So, for example, in this case, HCN will be detected in this source, which is NGC253, and another source of NGC253. So this is an example of a good correlation because it follows this line, this one line. The closer the molecules are from that line, the better the correlation is. And the better the correlation is, we can say that the chemistry of those sources is similar. However, if we have a bad correlation case, it means that we have like a cloud of points. There is no clear trend. It means that the chemistry is different in two different sources. However, this analysis is only by eye. So we would like to make a quantitative analysis by using correlation tests. We have used Spearman, Kendall-Stau, and Tailsane correlation test. But to simplify things, we have used this value, this M, which is the average of the other three correlation tests. And this value goes from 0 to 1. 1 is perfect correlation, and 0 is terrible correlation, as you can see here. And these values are the ones that we are going to use for reference to characterize the similarities or difference between different sources. So in the previous case, we can see now how this value is, the same value is pretty close to 1, which makes sense because this correlation is pretty good. And in this case, this is a poor correlation because it's more like a cloud of points, and the M value is 0.4, so it makes sense. Okay, so with all of this methodology presented, I am going to start speaking about my scientific articles. This is the first one that we published, which is called The Chemical Ingredients of a Massive Stellar Protocluster in the Making. Here, we are going to study a star-forming region. Why do we start with star-forming region? Because as I previously mentioned, there is a growing evidence that our sun was born in a dense stellar cluster surrounded by massive stars. So if we start studying a star-forming region, we will know the molecules available when our sun was born. So we selected this source, which is G3141, which corresponds to this stage of the solar system formation. So this is G3141, and why do we choose this particular source? Because it's one of the most chemically rich sources in our galaxy. Therefore, we will be able to retrieve a huge amount of molecules. Also, G3141 is composed of 4 protostars, four massive stars, which are A, B, C, and D, which is here. And these 4 parts will conform the central part of G3141. And we want to study the hot molecular core, which is the central part of G3141. Okay, but what is a hot core? A hot core is basically, it's all the area which surrounds these 4 protostars. So these 4 protostars will hit the nearby environment, and with this heat, it will trigger chemical reactions, and they will be dissolving this into space, and we will be able to detect molecules. Okay, so we have the star, and it's surrounded by dust grains. And the energy of this star is going to trigger more reactions into the grains. And once these reactions had happened, with this extra energy, also those molecules can be dissolved, can be ejected into the space. Because when we observe with ALMA, we are only detecting molecules that are into space. We do not detect molecules that are into the grains. And also, this extra energy can trigger some gas phase chemistry. They can make easier for those molecules to be interacting in the space. So how do we study this source? thanks to the WAPOS project. So WAPOS project is devoted to study this source with ALMA. And ALMA is basically studying this part, this black part, which is the hot core, which is the part that we are interested in. And we are covering full band 3, ranging from 80 for 116 gigahertz. We work at radio regimes, which means that we work with gigahertz. Okay, so this is the spectrum that we obtain with ALMA. It's really crowded with a lot of transitions, so we need the help of MATCUBA to characterize this source. So this is some outputs of some molecules that I was able to detect, in this case formaldehyde. And as you can see here we have 2 transitions characterized, and we have detected also some isotopologues. We have also detected cyanamide, and also molecules more complex, such as CH3SH, in which we have all of these transitions detected, cyanacetylene, for example, and we have detected also ethylene oxide. This molecule, which is quite complex, it has all of these transitions that all of them are pretty well characterized. And by the way, I didn't mention, but in red is the detected molecule, and in blue is the contribution from other species, and in black is the observational spectrum. So, how many molecules I was able to derive? In this case, we have 18 detected molecules plus isotopologues. This is the WAPOS 5, which is the 5 work of this project, but there have been more works previously that previously obtained all the molecular inventory. And in this case, we have a molecular sample of 38 molecules. So with these 38 molecules, we will be able to perform comparisons to compare the chemistry of this source with other sources. So we have studied and detected molecules here in E3141 hot core, which is a star-forming region. But we will be able to compare it with other well-characterized low-mass star-forming region and with respect to 2 comets, which represents this stage of the solar system formation. So we selected IRA 162932422BB, en fin, a long name. And then we have why we are interested in this source. We are interested in this source because it's a solar-like protostellar system. It's like our sun, but in the past, it's a small protostar. Also, we have selected 2 comets, 67P and 46P. These 2 comets are also deeply characterized, and we have a huge amount of molecules to compare. And 67P is famous because the spacecraft Rosetta landed there, and we have amazing in situ data. Okay, so let's start with the comparisons. What happens when we compare the 2 star-forming regions, the high mass, which is the one that we characterize, and the low mass? We can see how the correlation is pretty decent, is pretty good, which means that the chemistry is similar in 2 sources, but these 2 sources are physically different. They have different mass, they have different UV radiation and luminosity. So in this case, we are slightly changing the physical conditions, but it doesn't appear to be changing the chemistry that is involved. Also, we have compared, in this case, only nitrogen and oxygen-bearing species. And in this case, we compare star-forming regions and comets. And all the correlations are pretty good, which means that the oxygen and nitrogen-bearing species do not change. They are pretty constant in all the process of solar system formation. But what happens with the sulfur-bearing species? Sulfur-bearing species behave differently. As you can see, they are clearly below this one line, below this gray line, which means that, by the way, here we are comparing star-forming regions and comets. And as you can see, this implies that sulfur-bearing species are less abundant in star-forming region than in comets. To see the same thing more clearly, we can see how there is a bump here. Here, this is the abundance, the number of sulfur-bearing species that we have in star-forming regions, and here in comets. So there is a bump, which means that indeed we have less sulfur species in star-forming regions. And why is that? This is due to the sulfur depletion problem. So we believe that the sulfur is trapped on the grains. And despite all the stars hitting the grains, the sulfur-bearing species, they still remain in the grain. And only oxygen and nitrogen-bearing species are dissolved. And only when they are dissolved in the gas phase, we can detect them. So we think that the sulfur is there, but it's trapped in the dust grains. Okay, so to conclude the first paper, we have analyzed a large sample of molecules which in total of 38 molecules. We have detected how between low mass and high mass star forming regions, despite the different physical conditions, the chemistry is pretty similar. Also, we have derived how oxygen and nitrogen bearing species are pretty constant in all the stages, which means that the oxygen and the nitrogen are initially set and they do not change when the solar system is being created. And also we have the sulfur bearing species which behave differently, which may be due to the sulfur depletion problem. So the second scientific article, it's about the same source, but a different region. In this case, we'll be studied a shocked region. So we have studied this source, which is the hot core of G3141. And if you remember, this is a bunch of protostars just hitting the surrounding environment and warming the dust grains and creating some reprocessing on the grains, some triggering new chemical reactions. But what happens if we zoom out? If we zoom out, we see how there is a shock region, and we know it because PN and SiO are two typical tracers that will help us to derive what is a shock region. And this shock region, it's special. Why it's special? Because it is connected with the hot core that we studied previously. If you see these black lines, means possible outflows. So these four protostars, they are creating this outflow, which is directly connected with the shock region. So we think that these four protostars are ejecting material towards a zone which is more dense, and when this material shocks with that region, it creates this emission of these two molecules. But this is an interesting case, because we are having that the grains of these two sources are pretty similar because they all come from the same natal environment. They are interconnected. Also, we know that the temperatures are pretty different. A hot core, due to the thermal processing of all the stars, they have higher temperatures, 150 Kelvin. However, the shocks, their temperature is lower. It's about 10 to 20 Kelvin. Okay, so what happens in the shock regions? Here, we do not have stars involved, which means that we need another mechanism to desorb the molecules, to eject the molecules to the interstellar medium. So we have a bunch of molecules in the dust grains. So when these molecules collide, they collide and then eject all the grain mantle and then eject that to the interstellar medium. And when it's in the interstellar medium, we can detect them. So in this case, we have chemistry that it doesn't involve any kind of stars. So we have less processed material. Therefore, the material that we are observing, this material, it can be used as a proxy of the grain mantle composition. It's a way of seeing what is in the grain mantle composition. What is in the grain mantle, sorry. So when we extract the spectrum of this shock region, which is this one, we can see how it's really different compared to the hot core. Here, there is a lot of transitions, and here the amount of transitions is pretty low. But despite that, we are able to detect, again, molecules here. In this case, we have detected acetaldehyde, and if you realize, the spectrum is quite different. It's way more clear. There are less contaminations due to less transitions. We have acetaldehyde, formamide, or methyl mercaptan, among others. So when we performed the full study of this source, we were able to retrieve these molecules. So these molecules, again, we have a large sample of molecules of 34 detected molecules. So the strength of this thesis is that these numbers of 34, it's a large number of molecules only in one source. So this is one of the first times that we are using this amount of molecules to set the chemistry and then to compare with other sources. So the first thing that we are going to complete is we are going to compare the hot core versus the shock. We are going to compare what happens when these two sources, which are interconnected, which are G31, which are, sorry, the hot core and the shock region, and we see how the correlation is 0.5. It's decent, but it can be much better. Which means that the chemistry, despite all these molecules coming from the same grains because they are connected, this different chemistry, the shock chemistry, allow us to observe what are the molecules inside which are, in the grain mantle. So in this case, we have that the chemistry is different in shocks than in hot cores. So if we know that our shock region has a different chemistry, what happened with other shocks in other parts of the galaxy? So we have selected these sources because they have dozens of molecules detected. And these are different kinds of shock-dominated regions. We have low mass protostellar outflows, which is a low mass star, and with its outflow, it creates a shocked region. The same thing, but with high mass star. And then we have a molecular cloud, in which is dominated by large-scale shocks. So when we compare our shock region with other shock regions, we can see how the correlations are better. The lower is 0.4, but the highest is 0.8. Which means that the chemistry in our shock is much more similar to the chemistry of other shocks. So the shock chemistry in all of the galaxy is quite similar. And also, if we are detecting so if we have the grain mantle composition and these shocks erode the grain mantle and sends the molecule to the outer space, and we are detecting the same molecules in different shocks, it means that there is no gas phase chemistry, that the molecules barely interact between each other in the space, because otherwise the chemistry should be different. So to conclude this second work, we have analyzed 30 species of the shock region, that we have found a differentiation between hot core chemistry, between the chemistry of a hot core of a bunch of stars surrounding, hitting the nearby environment, and also between shocks, which means that the chemistry is different, and despite being connected, because remember that G3141 is the same source. We have only studied a hot core and a shock region within the same source, which means that it's more important the kind of shocks, the kind of physical environment that we have here to just characterize the chemistry. Also, we have compared with other shocks, and we can see how the molecular inventory is pretty similar. The correlations were good, and that means that the chemistry which is happening is pretty similar. That the molecules that are sticked into the grains, they are all pretty similar as well, independently on the location of the galaxy. So this is the last scientific article, and this article we are studying other galaxies. So all the previous sources that I showed, they are only focused on sources in our galaxy. So we want to go one step further. We want to go one step further, and we want to study what we call extragalactic astrochemistry. How are the molecules, how they behave, and how is the chemistry when we move to another galaxies? We would like to bridge the gap between the galactic and extragalactic chemistry. But we have a problem with extragalactic chemistry. The galaxies are pretty far, which means that the densities that we obtain are lower. So it's way more complicated to detect molecules there. Indeed, there are way less molecules detected outside of our galaxy. So to detect molecules in other galaxies, we have this project called Alchemy. So Alchemy is devoted to study NGC 253, which is the Sculptor galaxy, and is devoted to study it in detail with an amazing coverage. So the spectra that I previously showed you, it only includes ALMA band 3. In this case, we have ALMA band 3, 4, 5, 6, and 7. So it means that we have a huge coverage. So a lot of transistors can be there, and thus we can compensate the distance of the source. This is an example of the spectrum. So this is the NGC 253, and Alchemy was devoted to study just the central part. And the central part is this part over here. So in this part, thanks to this molecule, we know that there is 4 sources marked with black crosses in which the emission is more prominent, which means that we will that those 4 sources, they are good candidates to try to extract a good amount of molecules from there. And also they are this GMC stands for giant molecular clouds. They are molecular clouds, but really, really, really big compared to those ones in our galactic center. So this is an example of the spectrum of the brightest one, which is GMC6. And here we have a coverage from 80 to more than 350 gigahertz. This coverage is needed. We need it to try to compensate the distance of the source. So we perform again with MATCUBA, and we detect one by one all the molecules that we can, and we end with all these molecules detected. And the four sources, they have more or less the same amount of molecules detected. But the really important thing here is that we were able to detect 30 or more molecules outside of our galaxy, which is pretty unlikely. Other sources have only 5 to 10 molecules detected. And also, thanks to the alchemy data, we have detected for the first time 3 molecules outside of our galaxy. So, first of all, we would like to know what happened with the 4 sources inside of our galaxy, how they behave chemically. And we can see how the correlations are pretty good, are 0.8, 0.9, which means that the chemistry in these 4 sources inside the galaxy is pretty similar. Okay, so the fact that this galaxy is pretty far, it means that we do not know what kind of physical process determines the emission that we are detecting. In our galaxy, we can know if they are hot cores or star-forming regions or shock regions, but here we do not know. But now, thanks to this high amount of molecules, we have a unique opportunity, which is to know what is the dominant chemistry in other galaxies. In this case, we have compared with 2 star-forming regions and 2 shock-dominated regions. So when we compare our outer galaxy, NGC253, with respect to the two hot cores, we can see how the correlation is poor, is less than 0.37. However, when we compare it with shock regions, the correlation is way much better, which means that the emission that we are detecting is arising from shocks, from large-scale shocks. And also, a very important thing is like one of those shock regions is a molecular cloud in the galactic center of our galaxy. So we have that the chemistry, that the molecules are pretty similar in the central part of our galaxy and in the central part of other galaxies. And finally, now that we have this opportunity to use this high amount of numbers, high amount of molecules detected in this source, we would like to compare with other galaxies, with other extragalactic sources. But as I mentioned you before, the number of molecules available is way lower. Okay, I know that you probably cannot see the numbers because it's everything pretty smashed. But if you believe me, the M values, the values of the correlation, they are all about 0.7, except for this one, which is 0.4. This is the worst correlation, but it makes sense because this is not a galaxy, this is the Large Magellanic Cloud, and this is a hot core. And we mentioned that NGC253 is triggered by shocks, so the chemistry is different, and therefore the correlation is bad, so everything makes sense. And also, when we compare with the Star-Mass galaxies, AGNs and Juliers, we can see how all despite the low number of molecules detected, we can see how the chemistry is pretty similar. So in these sources, we can also say that all the chemistry is triggered by large-scale shocks. To conclude this last paper, I would like to say that we were able to detect 30 molecules in 4 sources in other galaxies. Also, that all of these 4 sources in the central part of the galaxy that we are studying, they are pretty chemically similar. Also, we have that thanks to the comparisons between our galaxy with the other galaxy that I was studying, we can now know that all the emission that we are obtaining, it comes from large-scale shocks. And finally, we can see how other galaxies, they are also dominated by large-scale shocks. And just the overall conclusions we have. In the first work, we studied that oxygen and nitrogen-bearing species, they remain constant in different phases of solar system formation. So they are set in the earliest stages, and they do remain constant. Then sulfur-bearing species, they behave differently. They have some kind of reprocess. Also, we compare a shock region, which is part of the same source as this hot core. They are linked, they are together. But the fact that it's a shocked region, it implies different chemistry. So we have seen how if we want to know what molecules were in are sticking to the grains, to use a shocked region, it's more reliable because